structure builds on the foundation of the object-oriented programming concepts of encapsulation and data abstraction, and it helps develop the notion of an abstract data type. As you probably know, a data type such as an integer or double is a group of values and operations on those values that is defined within a specific programming language. In contrast, an abstract data type, or ADT, is a specification for a group of values and the operations on those values that is defined conceptually and independently of any programming language. A data structure is an implementation of an ADT within a programming language, and this lecture also begins to generalize the idea of grouping objects together. A collection is an object that groups other objects and provides various services to its client. Various collections exist for different purposes, and we're going to specify the behaviors of collections abstractly. So a collection is an abstract data type. However, an abstract data type is not necessarily a collection. For an example of a collection and of an abstract data type, let's look at the abstract data type bag. A typical collection enables the client to add items, remove or retrieve items, and query the objects it represents. Let's look more closely at the specific behaviors our ADT bag needs. We need to check the bag's status, so we need to get the number of items currently in the bag and see whether the bag is empty. We need to be able to add a given item to the bag, remove an unspecified object from the bag. We need to remove an occurrence of a particular object from the bag if possible, and we need to be able to remove all objects from the bag, such as when we want to empty or clear the bag. We need to count the number of times an object occurs in the bag, and we need to test whether the bag contains a particular object. And finally, we need to be able to look at all the objects in the bag. We can take these behaviors and write them on a class responsibility collaboration or CRC card. Since a bag is an abstract data type, we only describe its data and specify its operations. We don't indicate how to store the data or how to implement its operations. For example, don't think about arrays. We first need to clearly understand what the bag operations do, not how to do them. That is, you need a detailed set of specifications before you can use a bag in a program. In fact, when we design ADTs, we should specify the ADT's operations even before we decide on a programming language. Before we can implement a bag in Java, we need to describe its data and specify in detail the methods that correspond to the bag's behaviors. We'll name the methods, choose their parameters, decide their return types, and write comments to fully describe their effect on the bag's data. Our eventual goal, of course, is to write a Java header and comments for each method. But first, we'll express the methods in UML, or Unified Modeling Language notation. As behaviors, our methods should begin with action verbs. For example, when finding the number of items in the bag, we get current size. This method returns the number of items, so it should return an integer type. It doesn't need any parameters since it operates on the bag itself. Similarly, isEmpty does not need any parameters. This method is only checking the status of the bag. As a predicate or yes/no question, it can return a Boolean value. To add an entry to the bag, we can call our add method. It needs a parameter of the type of object we're going to store in our bag. For now, we can use a generic T to represent that type. Here we have an interesting design issue. What should the add method do when it cannot add a new entry? At this point, we have two options. First, we could do nothing. We cannot add another item, so we ignore it and leave the bag unchanged. Second, we can leave the bag unchanged, but signal the client that the addition is impossible. The first option is easy, but it leaves the client wondering what happened. The second option is a better one, and it is easy to specify and implement. Displaying an error message is not a good choice, since a class should let a client manage all written output. Since adding an item is either successful or not, we could simply have the method return a Boolean value at this time. Later, we'll examine using exceptions to notify the client. The first remove is easy. We could just have it return the item removed. If the bag is already empty, our method can return null. Since the client doesn't know ahead of time what item is going to be removed, the return of an item is important. The second remove method requires us to specify an object to be removed. If the bag does not contain the item, we need to inform the client. Since the client already had to specify the item as a parameter, we can return a boolean to indicate whether or not the item was successfully removed. Removing all the bag's contents can be a void method. We just want to empty the bag, not retrieve any of its contents. The next two methods report on a specific item and don't change the contents of the bag. Then finally, we want to look at the contents of the bag. Rather than providing a method that displays the entries in the bag, let's define one that returns an array of these entries. The client is then free to display any or all of them in any way desired. This design decision makes our class more portable and independent of display methods, such as needing to determine if the application is console or GUI based. As our specifications become more detailed, they can increasingly reflect our choice of programming language. At this point, we can write Java headers for the bag's methods and organize them into a Java interface for the class that will implement the ADT. Remember that a Java interface does not have fields, constructors, or private methods. For now, the items in the bag will be objects of the same class. For example, we could have a bag of strings. To accommodate entries of any one class type, the bag methods use a generic type T for each entry. To give meaning to the identifier T, we must write T in angle brackets after the name of the interface. Once the actual type is chosen within a client, the compiler will use that data type wherever T appears. Here's the syntax example implementing the generic interface bag interface. The class bag must provide an implementation of all the methods we're about to define in the interface bag interface. When we're ready to instantiate or create a bag object, we specify the type of the item we want to store in the bag. In this example, we're storing string objects in our bag. Our methods that check the status of the bag are independent of the type of items stored in the bag. The add and remove methods use the generic type T for the entry to add or remove from the bag. Since we're not worried about implementation details yet, how these items are stored and removed is not important to us. And last, we have the methods that check the status of a particular entry stored in the bag and the toArray method that returns an array containing the entries in the bag. Just because this method returns an array of the entries does not imply that the items are stored in an array data member of the ADT bag. How we store these data items is an implementation detail and the topic of another lecture.